Maybe. Yeah. So the high resolution camera. Okay, it's online learning. What lecture notes section does this? I haven't got the lecture notes written yet for this week. So usually I try to post them in advance, but I'm behind. I still haven't finished the fast Fourier transform notes, and that looks like the little camera looks like it's crooked. But okay. We're just gonna have to go with that. Maybe. Is that better? Also, I have. Maybe not. Yeah, okay. So no lecture notes yet. But this stuff is very classic. So it's the way I was teaching Huffman's algorithm. I haven't actually seen anybody else teach it that way. So that's a bit new. Minimum spanning trees. Okay, I'm going to do a third algorithm, so we are recording here, which is a bit unusual, because most people in the book, they just cover Kruskal's and Prims. I'm going to cover Kruskal's, Prims, and Boruvka's, which is not much different, but requires a little bit of thinking about data structures. Yay, data structures. Okay. So people have said you can't really see this graph. Maybe it will be better if I go over it with the new black marker. So before we do that, a little bit of background on minimum spanning trees. These are greedy. The minimum spanning tree algorithm construction algorithms are greedy algorithms. They're sort of the classic greedy algorithms. In the book, they start, I think, with interval scheduling, which is super easy. Minimum spanning trees are not quite that easy, but they're easier than Huffman's algorithm. I mean, Huffman's algorithm is pretty basic, but the proof of correctness is not obvious. That's why probably Shannon didn't see it, and Huffman, it took him a while. So the arguments for the proof of correctness require a little bit of graph theory. But that's good because I think you've seen graph theory before, a little bit. And it will get us into this mode of the standard form for proof of correctness of a greedy algorithm always goes, before we do, remember for Huffman's algorithm, we had my friend Jeremy who was going to show up for the sorting stuff, for the merging the sorting list. We were going to have to try to do the first step by ourselves, and then Jeremy was going to show up and say, okay, I can take it from here. You haven't messed things up terribly. I can still reach an optimal solution. So today I'm going to pound this in that the argument goes, okay, before you have taken any steps, your empty subsolution can be extended to an optimal solution. Okay, imagine that after I steps, your subsolution, your current subsolution, can be extended to an optimal solution S. Show that now you make this greedy choice for your I plus first step. Show that your subsolution after I plus 1 steps can still be extended to an optimal solution. Maybe the same one, maybe also S, or maybe S prime. And usually how you do this is called an exchange argument. So you say, okay, well, if I do something, so after I steps, my subsolution could be extended to S, which is optimal. Now I take another step, after I plus 1 steps, maybe S didn't do the same thing on the I plus first step, but whatever S did, I can sort of take S and change it around and say, okay, I still get an optimal solution, S prime. So this is the exchange argument. Now you don't have S, obviously. S is an optimal solution. If you had an optimal solution, you wouldn't be doing this. But this is how you argue. So you say, okay, before I do anything, I haven't messed up. Suppose that I haven't messed up to the ith step, then I show that on the I plus first step, I don't mess up. Then by induction, I don't mess up. Okay, so it's like, you know, before we do anything, Jeremy can come and fix and Jeremy can come and find an optimal solution. The other way around, S can be modified into S prime. I mean, technically, okay, you can do it the other way, because you just do the reverse thing. But we say that S can be changed into S prime. Okay, so we're going to see 3 examples of these proofs. One which is the first proof of granting is pretty easy. The second one is not so easy. The third one is just like the second one. Okay, so let's go with Kruskal's algorithm. Okay, so if people want to look this up in the index or something. Oh yeah, this is much easier to see, right? Kruskal's algorithm. Okay, so minimum spanning trees, you have a graph, and the edges have weights, okay? So you can imagine that you are like a county planner and you have a bunch of little towns and they're connected by dirt roads, and you want to pave some of the roads such that you can get from any town to any other town only along paved roads. Now each road has a cost to pave it, and you want to pave it such that you spend the minimum amount of money. Okay. Now this comes up, that's usually the kind of motivation you give, but it also comes up, for example, where you just want to connect everything and you don't care about sort of redundancies or latencies, like how long it takes you to get from one town to the other along the paved roads. You just want everything to be connected. So, okay. So you can also imagine, for example, you're setting up a lighting display, and you want to have power to all of the lights, and so you want to put cables, and once things are connected, it doesn't matter if sort of how far they are from the source, they still get power. So, I mean, like, there are advantages to using serial and parallel connections and stuff, but whatever. Okay, you're a Christmas tree and you want all the lights to come on. Okay? Now, so this is the problem. You want to find a subgraph that connects everything. So this is why it's called spanning. It's a tree because if you had a cycle in it on Minecraft Redstone, okay, I'll take your word for it. If you had a cycle, you could take out one of the edges and not disconnect anything. So the minimum cost, as long as the weights are positive, the minimum cost subgraph that connects everything is a tree. So it's a spanning tree, and you want it to have minimum cost. So it's a minimum spanning tree. Okay? So this is your job. You have to find one of these things. Okay, so if we had more time, I would actually do this whole Socratic method thing, and like we did with Huffman, saying, oh, well, what are you going to do first? But just to sort of plow through Kruskal's, and also because there are lots of different minimum spanning tree algorithms. I'm only going to show you, well, I'm definitely going to show you 2, maybe I'm going to be able to show you 3, and because I also want to get to how you implement these things, which is also very cool. Kruskal's, I don't know if you can, okay, so I'm going to go through this again. Oh, I spent all that time drawing this stuff, and now, well, it's not that hard to redraw. So this is A, B, C, D, E, F, G, This is 4, 11, 8, 1, 2, 10, 9, 14, 4, 6, 2, 8, 7, 7. Okay, not sure if is that easier to read? And this line also exists. Easier to read? Okay. So it's environmentally friendly. Environmentally unfriendly. I'm using up more markers, but it does make things easier to read. Okay, so Kruskal's algorithm, what you do, you take all of the edges and you sort them by weight. And you take, by increasing, non-decreasing weight, and then you're going to take you're going to process them in this order. And for each edge, you're going to take it, and if you can add it and it doesn't break your tree. So breaking a tree well, actually, you're not going to have a tree. You're going to have a forest. A collection of trees is called a forest. This should be easy to remember. If you add it and it creates a cycle, then it breaks your forest. So you're not going to, you can't add it, you throw it away. It's incompatible with your sub-solution so far. If you can add it and it doesn't create a cycle, then you add it. Okay? So let's just run through Kruskal's algorithm. What is the cheapest edge? Anybody? It is the edge with cost 1, right? H to G. Okay, okay. Yes, H to G. Yes. Okay. Does it create a cycle? No, because we don't have any other edges yet. So we're going to add this. Okay, can you see that? Is it red? Yes, okay. Okay, what is well, there's actually a tie for things with cost 2. So which one do we want to, whoever speaks first gets to choose which of these, I to C or G to F. G to F, okay. G to F. Okay. Now, did it create a cycle? No, we added. Now, the next one is I to C. Does it create a cycle? No. Can I make that I capital? Okay, well, I'll just redraw it a bit bigger. Okay. Okay. So, does it create a cycle? No. So we add it. So, what can we add now? Is there anything with weight 3? No. There are 2 with weight 4. What do people want? A to B. A to B. Okay. Okay. Now, there is another one with weight 4. I should actually be checking. They have these steps in the book. Another one with weight 4. Okay, is there anything with weight 5? I don't see anything with weight 5. Is there something with weight 6? Yes. Do we add it? No, we do not. C to F. Where is C to? 4, okay. We do not add it because if we did, it would create a cycle, and that would break our solution. So we do not add it. So this, no. Now, is there anything else with 6? No. Is there something with 7? Yes. Does it create a cycle? No. C to D, yes, okay. Now, anything with weight 8? Yes. There's this and this. Which one do people want to look at first? I has 7. Oh, right. Sorry. Yes. We have to process this after this. So we look at this, does it create a cycle? Yes, because it would create a cycle like that. So we don't take it. Now there are two with weight 8. Which one do we want? A to H. Okay. Does it create a cycle? No. So now the next one is B to C. Now if we hadn't done that, we could add it because it wouldn't create a cycle. But since we have this, if we add this edge, it creates this cycle. So we can't add it. Okay? I should have written Kruskal's over here. Now what? There is nothing else with it. Okay, weight 9, D to E. Yes, does it create a cycle? No, okay. We add it. Okay, now 10. 10 is E to F. Does it create a cycle? Yes. We don't add it. 11, B to H. Does it create a cycle? Yes. We don't add it. And then 14, D to F. Does it create a cycle? Yes, it creates a triangle. So we don't add it. So our tree looks like this. Okay, does it connect everything? Yes. So it's spanning, it's a tree, it's a cyclic, and we believe that it's minimum. For something, not sure what. Okay, so how do we prove it's minimum? So we're going to use this template for proofs of correctness for greedy algorithms. I'm just going to see how much. I have to keep this timer because I think if I 7 minutes. Okay. So before we process any of this, so the edges were in this sorted order, right? So we're going to put the edges. So the edges were in order. I could write them out, but that would take. Okay. So before you do anything, you sort the edges, and before you look at any of the edges, your subsolution, your forest, has no edges in it. So you can definitely add edges to get an optimal solution. So before you look at any edge, when you look at an edge, you decide either to take it or to throw it away, and irrevocably. You can't change it once you've made that decision. So before you look at any edge and you make any decisions, you haven't made a mistake. Okay? So before we take any steps, are empty subsolution can be extended to an optimal solution. Suppose that after I greater than or equal to 0 steps, our subsolution can be extended to an optimal solution S. So at some point we've processed I edges, we've made decisions about these I edges, we've kept some, we've thrown some away, and we have a forest, okay? And now we're going to process the I plus, and we're assuming that after I steps, our forest can have more edges added to it to get a minimum spanning tree. Now we want to say, now we're going to process the next edge in order by weight, and we're going to either keep it or throw it away. So I have to get rid of this. Everybody look at this. I'm going to keep this because I'm going to use it, draw it again. Where is it? Well, do I need it? I can just look at the book again. Okay. So, we're looking at the ith edge. Sorry, I plus first. The I plus first edge in non-decreasing order by weight. Cost. Okay, now, if we look at it and we throw it away, is that this is I greater than or equal to 0? Okay, yeah, so greater than or equal. So the base case we're taking care of. After 0 steps, we haven't messed up. So if we look at this edge and we throw it away, we would only do that if we can't add it to our subsolution without breaking the subsolution, without creating a cycle. Right? Because we look at it, if it creates a cycle, we throw it away. If it doesn't, we add it. So if we throw it away, then it created a cycle. With our subsolution. Now notice that S, this optimal solution, contains our subsolution as a subgraph. All of the edges we've already taken are in S. All of the edges we've already thrown away are not in S. So if we can't take the edge, then S doesn't contain the edge. So it created a cycle with our subsolution, and so also with S. Okay? 55 seconds. Okay. So S doesn't contain that edge either. Okay, in that case, we get what we want. I plus 1 steps. We've shown that if we throw it away, then after I plus 1 steps, our subsolution can be extended to, an optimal solution S prime. So if we throw, which in this case S prime is just S, because if we throw the edge away, S couldn't have contained it either, so after I plus 1 steps, we can still, our subsolution can still be extended to S, okay? Now, here's the tricky case. Suppose we, which is not so tricky, suppose we take the edge, okay? Now, it's not guaranteed that S has to take that edge. Remember, there were, oh, perhaps I erased it. There were those 2 8s, right? And if we took one, we couldn't take the other, right? So we took the one here, so we couldn't take the one here. So maybe S took the other one. So how do we argue that even though we differ with S on what we've done with this edge, we've taken it and maybe S throws it away and takes the next one, which we can't take. How do we argue that you can, and so, what comes after so? And so also with S, here? Yeah, okay. If we throw the edge away, then it created a cycle with our subsolution, and so also with S. So S, okay. If we couldn't take it, S couldn't take it either. Okay, so what if we do take it? So, well, we're just worrying about this one thing. We've taken this one edge, and S hasn't, and now we're going to say, okay, but then we could take S and change it around so that it contains this one edge that we've taken, and we haven't increased the cost. Okay? So the argument to this is, I just have to remember that I'm teaching you, yeah, this is, yeah, Kruskal's, I'm not switching up Kruskal's and Prims. This is Kruskal's. Okay, so suppose we take the solution S. So S is a tree. Okay, and now, so what we're going to do is in green, let's put the edges. Okay, so I'm going to do this a little bit differently. I'm going to draw in green the edges that we already have taken. Okay, which are a forest, little trees. And then in black, we're going to show the edges that S takes to complete our okay. Okay, so in green are the edges that we have already taken. In black are the edges that S takes to complete the solution. And in red, which is unfortunately covered with black at the moment because I was writing over black edges. In red, can you see that? Can you see that it is red? It's pretty red. Yes, okay. So in red is this edge that we take that S didn't take. So imagine you take that edge and you put it into S's solution. It's going to create a cycle. Now, going around that cycle, consider the black edges on that cycle. Okay? I'm going to argue that one of them has to be, one of the black edges has to be at least as costly as the red edge. Why? Well, if